All right, hello everyone. Today is June 13th. Hello to my synchronous learners. Hello to the asynchronous learners. If you are asynchronous, remember that the homework due dates are still your responsibility to get those turned in on time. So I just want to point that out there. I'm pretty lenient, pretty flexible. I know it's the summertime, so I know you have jobs. I have jobs, and it's a lot of stuff going on. You may have families and other obligations, and I have the same thing too. So I get it. I'm a student too, so everything that you guys are doing, I'm doing too. Kind of wish my professor is more like me, but that's so. I think you guys are pretty lucky, in all honesty. So why don't we go ahead and get started? And I want you to succeed. I don't want people not to succeed. So if you put in the time and effort, I generally want you to succeed. That's why, the test, if you haven't started it already, you get 3 hours to do the exam. It doesn't take that long. You'll find out. But in case you have any internet hiccups, that time is there. So make sure you're at a stable internet connection. The exam is due Wednesday at 11:59 p.m. So, you have now until Wednesday at 11:59 p.m. So don't wait till 11 o'clock at night on Wednesday night to take the exam. I mean, you can wait till Wednesday, that's fine, but don't be, make sure you give yourself the full time to complete the exam. So at the latest, you'd want to start the exam at 9. I mean, if that's if that's what you had to do, I would start it at 9. That way I could have the maximum amount of time. Otherwise, if you start at 11, that exam is still due at 11:59. So you'd only give yourself, an hour to get the exam done. So, please don't put yourself in that situation. As far as homework goes, we talk about the homework due dates in class. We do the homework. So, there's really should be no excuse not to get the homework done. I did have a couple emails, requesting more time, but I'm not lenient on that, and only because we solved the homework in class. I put it on your responsibility to get it done, and you generally send out an email, regarding when the homework is due. So, just please, watch the lectures if you are listening to asynchronous. Try to watch them the same day. So if I am working right now, I might watch the lecture at 8 o'clock at night or whenever is convenient for you. So I just wanted to throw that out there. So I'm going to go ahead and share my screen. So in this chapter, we're going to talk about, reactions. To be honest with you, we're going to talk about substitution reactions, elimination reactions, and we've kind of already started talking about them in previous chapters, but we're going to really go into them in this chapter. Well, let me make sure my pen is working. There we go. So generally, here we have an sp3, sp2, sp would be a triple bond, which they don't show. So what is the hybridization of each highlighted carbon? They tell you sp3, sp2, and sp2. What structure represents an alkyl halide? They all represent an alkyl halide because they say X can be, chlorine, bromine, or iodine. I mean, if it was fluorine, that'd still be an alkyl halide. So it's just kind of an introductory slide. And they're saying that alkyl halides undergo substitution and elimination reactions. And this whole chapter is about substitution and elimination. So they figured you probably should know, what an alkyl halide is. For this one, alkyl halides can undergo a substitution reaction when reacted with a nucleophile. So, when we're substituting, we're replacing this X with this nucleophile. In general, it's going to go like this, and this is going to be gone. Elimination, maybe there's a hydrogen here, or, there's hydrogen here, and it's going to take that. It's going to form this double bond right here, and it's going to be a good leaving group. How they show it right here, though, they show it taking this hydrogen, and it's going to come here, and it's going to go. And you can see that double bond is right there. But, this is same stuff on all sides. So the double bond could have formed here, it could have formed there. There's no special reason why it formed right there. So alkyl halides can undergo elimination reaction when react with a base. What the nucleophiles and bases have in common. If you look at them, what do they have in common? They have a lone pair of electrons, right? So they have a lone pair of electrons, and we can see that right here for the base. We can see that for the nucleophile. And think about the nucleophile like a carbanion. It's going to come in here and do what it needs to do. Doesn't have to be a carbanion, it could be a halide too, like bromine, or it could be chlorine, and here's bromine, and that bromine is going to come in and it's going to replace that bromine. So just wanted to give you some ideas of what's going on. So when the reagent can act as a nucleophile or a base, elimination and substitution will be competing. So you can see here's our elimination product. And how do we get that? Well, we have this. So we have an elimination, and our substitution would be, it's going to be substituting. The two main reasons why alkyl halides undergo substitution and elimination reactions. The halogen is electron withdrawing. So here the X is some type of halogen. So either chlorine, bromine, or iodine. That's going to create it. So let's just say this is bromine. That's going to be drawing all this electron energy, isn't it? Making it susceptible to a nucleophilic attack. So they call this the alpha carbon right here. Now, let's just, for instance, instead of a hydrogen here, this would be a carbon. This would now be the beta carbon. Okay, so when you see alpha beta, hopefully that makes more sense. And the halogen acts as a leaving group. So, okay, so the bromine is going to act as a leaving group. And for a substrate to undergo a substitution or elimination reaction, and this is the substrate right here, it must possess a good leaving group. So that's our substrate. And it does have a good leaving group, right? The bromine is a good leaving group. Any questions so far? Okay, good. So that means you're understanding everything. Let me just check the chat. So good leaving groups are the conjugate bases of strong acids. So these are good leaving groups. You can see that they are the conjugate base of a strong acid. Remember, the strong acid have a very low pKa. So as we go down, if you look at chlorine, bromine, iodine, it goes in the opposite direction, doesn't it? So the best leaving group would be iodine because it has the lowest pKa. And the weakest acid, this is a weak acid, this is ammonia. Has a pKa of 38, and it'd be the worst leaving group. So that means if we have, let's just say, for instance, we had this. We're not going to really replace that, going like this. It's not a good leaving group to be replaced. If we think about this, carbon is more electronegative than nitrogen. So, we're basically doing something that's not going to happen. This is not going to happen. So alkyl halides are compounds with a carbon group is bonded to a halide. We talked about that. They're going to go over some naming of the compounds. So this is some review. So if you didn't understand it the first time, hopefully, second time through, this will help you out. So it's always good to have a refresher. And if you haven't taken your exam, this will be a refresher too. So this is propane. It has 1, 2, 3. And at the 2 position, we have a chloral group. And it says, convince yourself that they are numbered in the most appropriate way. So, I don't have to convince myself, but you have to convince yourself, that this is the way it should be. We could have started here on the opposite end, but then we started at a 4 and we want to start at the lowest number. So that's why we started at 2 bromo, 2 methyl pentane. B comes before M. That's why the B is out in front. Here, this is R, 5 bromo. So this would be 1, 2, 3. There it goes clockwise. That's R. And at the 5 position, we have a bromine, and the 2, 3. And at the 2 and 3 position, we have methyls. So we have a trimethyl, and this is a heptane. So I'll just park it right here so you can think about that and convince yourself that, the naming schemes are correct, which they are. All right. So some simple molecules are also recognized by their common names. There are common names such as chloroethane, ethyl chloride, methylene chloride, and dichloromethane. It's just the common names that people have used. So I don't want to spend too much time on naming. If you have any questions, just let me know. We can talk about it after class. So Greek letters are often used to label the carbons of the alkyl group attached to the halide. Recall, I said, this is the alpha carbon right here. That's the carbon with the first substitution. And then going out, here's your beta, and now you get to your gamma. So if there's another carbon here, this would be gamma out here. It says the amount of branching at the alpha carbon affects the reaction mechanism. So here we have a primary. Here we have a secondary. What do we mean by secondary? So this is our alpha carbon. We have 1 carbon, 2 carbons, and here's my alpha carbon here, and we have 3 carbons. And that R group could be more than 1 carbon, but we're just saying that instead of a hydrogen, this is a carbon right here. So some alkyl halides are used as insecticides. So, they're trying to get rid of some pests. For the insecticides below, label each halide as either primary, secondary, or tertiary. For the circled atoms, label all the alpha, beta, gamma, and delta. So delta would just mean 1 more carbon out from the gamma. So if this is your alpha, beta, gamma, delta, and that's all that meant. So they're talking about, how halides appear in a wide variety of natural products, synthetic compounds, DDT, which is banned, can be in some dyes, drugs such as anti-cancer, antidepressant, antimicrobial, food additives, and many more different products. So a substitution reaction requires the loss of a leaving group. Okay, and we talked about, what a good leaving group would be. It'd be a really strong acid, and its conjugate base would be a really good leaving group. So the best leaving group that we saw was iodine. There are two possible mechanisms, a concerted and stepwise. So concerted means everything's happening at once. Okay, so all this, so the breaking of the bond, this is the breaking of the bond right here, right? And making of the bond, this is the making of the bond, is happening at the same time. Stepwise would be, if it was stepwise, step one would be this, and then step two would be here. And the reason why it's concerted, otherwise we would have, they can sometimes show concerted reactions like this. They'll show it as dotted lines, and this is be a dotted line because we can't have 5 bonds to carbon at once, typically. So here they're showing you the stepwise, here's step 1 and step 2, the nucleophile coming in. Remember, now if this left, this is a carbocation, right? So we have a carbocation right here. And what's the, is this a primary, tertiary, secondary, tertiary? This would be a tertiary carbocation. So this is pretty stable. Now, if this would have just been like this, where we have just all hydrogens, it's going to happen more in a concerted, because think about this, there's sterics involved with this. That's why they're showing this reaction happening in this direction. There's no sterics happening like in here. So this is more likely going to be your SN2 or concerted reaction. And this is your stepwise reaction here. And they go on to say, what is SN2 on the next slide? And that stands for nucleophilic. It's a bimolecular. That means there's 2 chemical species happening at the same time. So it's substitution, nucleophilic bimoleculars, SN2. But that's on the next slide. So any questions about this slide? It says, what does the SN2 stand for? Substitution, nucleophilic, and 2 means bimolecular. There's two chemical species. Here's one chemical species. Here's a second chemical species. Now, an SN1 basically does the same thing, but it's unimolecular. That means, it's not concerted. It's going to be going on a stepwise. So, we're only going to be dealing with one species at a time for an SN1. But with an SN2, we have 2 chemical species that we're dealing with at once. Says, how does the observed stereochemistry, basically, okay, we have some base here. It's going to come in and it inverts itself. You can think about this like this. Okay, I'm going to try to draw my best, but it becomes a flat plane. And like I said, I'm going to try my best. So imagine all this stuff being a flat plane. And that bromine is going to come right here. And the reason, if you read the book, and I did read the book before I came to class today, The reason why, the sulfur, you could say, well, why doesn't it attack over on this right-hand side, right? Well, that's because you have this bromine in the way, and that's what the book says. So, with that bromine in the way, you're going to be more likely to go on the left side attack. If you do a left side attack, you're going to get an inversion. What do we mean by inversion? This methyl group is going to go over there, and you can see that right here. And that hydrogen and this ethyl group is going to, it's like an umbrella. It just inverts. That's the best way to think about it. It's an umbrella. If you have a wind pushing against that umbrella, if we have an umbrella, we have wind. That wind is going to flip that umbrella this way. And the same thing happens right here. So I believe next Monday is a holiday. So let me just check when that federal, it's Juneteenth day. So let me see. Juneteenth is actually on a Sunday, but I think the day we get off is a Monday. I'm actually gonna have to check that. I might check that during our break. So the nucleophile attacks on the backside, and we talked about that. That's because, why, how are you going to attack? It's easier to attack from this side. And I'm drawing silicon. I'm not supposed to be drawing, we want to be drawing sulfur. And we don't have any bromine right here. So that's why we're attacking from the backside. So from the HOMO, so what does HOMO stand for? Highest occupied molecular orbital, to the LUMO, which stands for lowest unoccupied molecular orbital of the electrophile. So this would be our electrophile. I'm just going to call it E. This would be our nucleophile. I'll call it N. And you can see that node right here. So that's another reason why this is not going to take place. So I know that's a lot going on. So, study the slide a little bit. So draw the transition state for the following reaction, which explains why SN2 reactions proceed with inversion of configuration. And what they're trying to tell you right here is, remember that little flat pancake thing that I drew on, we have the hydrogen, methyl group, and ethyl group. Now you're going to draw your sulfur group coming here, and that bromine group is going to be leaving. So that's what they mean by that. That's your transition state. So less sterically hindered electrophiles react more readily under SN2. So this is think about this, is the most reactive. There's no sterics involved with this methyl halide. And as we add more, R substituents, it becomes, a worse contender to be for an SN2 mechanism. So this would be the worst one right here, tertiary. This most likely is going to be your SN1, because this is going to leave first, and then you're going to have your nucleophile come in. It says to rationalize this trend, examine the reaction coordinate diagram. And this has to do with sterics. Here's a reaction coordinate diagram right here. You can see here it'd be your, if we just look at here, here's your primary, secondary, tertiary, here's your methyl group. And the relative rate is 145 versus 1 versus 0.008 versus it's not going to happen. This is alpha substitute. Now, if it's beta substitute, that means it's, alpha. This would be your alpha carbon, not your beta carbon. It's even further away. Sorry about that. Alpha beta. So that'd be even further away. And note that, that we are still at a 1. That's the same. This one is the same as this one. It says the beta carbons hinder the backside attack of the nucleophile, resulting in a slower rate of reaction. And to rationalize this, we must examine the energy diagram. So what feature of the energy diagram is relevant to rationalize the rate of the reaction? It's the activation energy. So now we're going this way. You can see that this is going to come in. This reaction is going to readily happen. I can just tell by looking at it. You have a carbanion, you have a good leaving group. This reaction is really going to complete, and they show you the transition state. So it's an exergonic, it's gonna proceed in that direction, SN2. It says which reaction will have the fastest rate of reaction right here. You tell me. And they did a good job good job with this diagram. You can see the lower the activation energy, the less energy it takes to overcome, the less. So the lower the activation energy, the more likely it's going to happen. So here you can see a difference of activation energies between here and here. And here we see that, we have a secondary versus a primary versus just a methyl group. It says tertiary carbons react too slowly to measure. That means that the energy diagram would be something like this for a tertiary. So it says, they just give you an example, of what might happen, You know, if we have a certain organic molecule. If you think about this, you know, you have CH3. You have to really think, you know, is it going to be an SN2? Is it going to be, I'm going to guess that it's going to be slow because you have all this sterics going on. So what are the factors that contribute to the strength of a nucleophile? A strong nucleophile is needed. Remember, it's a strong acid, so it have a, you know, if we go back to the first slide. Sometimes it's good to do this. We look at the conjugate base of a strong acid. That'd be a good nucleophile. Well, that'd be a good leaving group. So that's not what I want to say. The next slide talks about strong nucleophiles and weak nucleophiles. So you should be able to determine if the nucleophile is strong or weak. Which of the nucleophiles shown would have preferred to be SN2? You know, these would all go SN2 right here. It says in general, anions are strong nucleophiles. We all see that they're anions. Polarizable atoms. What does polarizable mean? Let's just say we had, you know, the electron density. Now here we have more electron density on the carbon than we do on the nitrogen. Likewise with this oxygen and this sulfur. And the solvent affects nucleophilicity. That means, what does that mean? That means if we had this methyl halide, and let's just say we want to react it with this base. Well, let's pick something, it doesn't matter. Let's say we want to react it with this. If we have water, that's going to solvate this chlorine ion here, right? Because this would be, you know, negative, and we can point the hydrogens in that direction, and it can solvate around that. So you have a bunch of water surrounding that chloride anion. If I go back to the previous, so a strong nucleophile, they talk about this, and you can see, you know, all the characteristics that we talked about. Polarizability, you know, we have an anion. Even though we have the same leaving group, you know, we have different nucleophiles. And here's the reasons why. So when an alkyl halide is treated with a strong base, it can undergo beta elimination.
Hey, I'm in class. What's up? Hold on. I'm in class.
To form an alkene. So a strong base will react in a concerted mechanism called an E2. That's an elimination. Bimolecular, it involves two chemical species. Here, base is going to attack right there. It's going to grab that proton, and then we're going to form that double bond here. And that X group, you know, you can think of X maybe as chlorine, bromine, or iodine. That's going to be a good leaving group. So this can be some type of good leaving group. It doesn't always have to be a halide. So here's your alpha, here's your beta. So we're attacking the beta hydrogen, or we're grabbing the beta hydrogen. We're forming that double bond between the alpha and beta carbon, and that halide, let's just say it's a halide in this case, is a good leaving group. And now we formed an alkene. All right. Any questions on that? Okay, we'll go to the next slide then. So E2 elimination is concerted. That means, you have everything happen at once, where the base removes a beta proton, causing the loss of a leaving group and the formation of a carbon-carbon double bond. So concerted elimination is bimolecular and follows second order kinetics. Well, it says in what ways they both involve two chemical species in a concerted method, right? One involves an elimination though, and one involves a substitution, but they both involve two chemical species at once. That's what they're getting at right there for that question. We consider a reagent such as sodium hydroxide, which is a strong nucleophile and a strong base. Hydroxide function as a nucleophile. So it's going to prefer the base, the elimination in this case, because of sterics right here. It's sterically hindered. That's why it's going to act as a base in this case. And LG stands for leaving group. So because of steric strain, cis isomers are generally less stable than trans. So here, here's your cis, same. Here's your trans, opposite sides basically. You still have your hydrogens that are not shown. And that's due to steric strain. And look at the trans, the steric strain is relieved right here, isn't it? And then to prove this, they're going to say, look at the heats of combustion. This is lower in energy right here. It's not, it's lower in energy by 4 kilojoules per mole. You take 2686 minus 2682, that's a difference of 4. And this is your trans. it's your cis, and it takes 4 kilojoules less. So, it's more stable. And you can see this difference right here. So alkyl groups stabilize the carbon-carbon pi bond via hyperconjugation. So more alkyl groups equals more stable alkene. So the tetrasubstituted would be the most stable if we go by, with these rules. It says in cyclic alkenes with less than 7 carbons in the ring, only cis alkenes are stable. That's because if you drew this, like this, you'd put a lot of strain. If you can just imagine this and then come in like this, there'd be a lot of strain right there. It'd be an elongation. So that, that's why that's not happening. So we do not need to indicate if the alkene is cis or trans unless the ring contains 8 carbons or more. When applied to bridge bicycloalkenes, this rule is called Brett's rule. We'll go on to the next slide. And why is this compound not stable? Well, 1, 2, 3, 4, 5, 6. And we go back to the previous slide. And cyclic compounds with less than only the cis alkanes are stable. So, and here we have 8. That's why this compound is stable. If we drew this double bond right here instead of right here, this would work. Okay. Or if we could have drawn it right here, drawn it right there, but we can't have it right there. But now in this case, we relieve the strain. How did we relieve the strain? We added more carbons. That's how we relieve the strain. So it is common for a substrate to have more than one beta carbon that can be deprotonated by a strong base. And so E2 elimination results in more than one alkene. It says when ethoxide is used as a strong base, this would be your ethoxide. 2-methyl-2-bromobutane gives 2 E2 products, and they give us the 2 products. With a more stable alkene, the Zaitsev product produced as the major product, and the less substituted alkene, which is the Hoffman product, is the minor product. And what they mean by more substituted is more stuff coming off this double bond. So here we have 1, 2, 3. So that's a tri-substituted, or it's only a di-substituted. So that's what they're saying right there. So, and remember, we just talked about that. The more substituted, the more its stability increases. So increases stability with the higher substitution. we're looking at a tri substituted versus a di. So we're going to pick the tri over the di. And that's what we did right here. And you can see that we get 71% versus 29%. And you don't have to memorize the exact percentages because that'd be impossible. You have to experimentally measure the stuff. Any questions on this? Hopefully this makes sense. And let's just count how many carbons and hydrogens we have with these products. Maybe that's a good thing to do. So we have 1, 2, 3, 4, 5 carbons here. 1, 2, 3, 4, 5 carbons here. 5 carbons, and let's count how many hydrogens we have. Maybe someone can help me out. 3, 3, 3, and 1. So that'd be 9, 10. And let's count how many hydrogens we have here. We have 2, 3, 3, 2. So 3 plus 3 is 6, 8, 10. 10 hydrogens. 5 carbons. So both have 5 carbons and 10 hydrogens. That means they are constitutional isomers, right? So what this slide is saying is, okay, we can kind of control, even though this is the more substituted, tri versus di substituted. And how do you get di? Here's 1, 2. Tri substituted would be, 1, 2, 3. So when constitutional isomers are formed as a product of a reaction with one of them as a major product, the reaction is regioselective. So this is the major product. So using this reagent, we have regially selected which product that we want. So it says the regioselectivity of an E2 reaction can be controlled by carefully choosing the strong base used. So depending on the base, depends on, which direction we're going to push this reaction. So we can push it towards the Hofmann reaction. If we use something, that has a lot of stuff coming off of it, like this right here, we can get the Hofmann product. It says experimental data. So they experimentally had to determine this. Indicates that a bulky, sterically hindered base will favor the formation of the Hofmann product. But an unhindered base, such as the ethoxide, will favor the Zaitsev product. So even though this is, less stable, not as stable as the tri-substituted, we can still get this di-substituted product. I shouldn't call it tertiary. I should just call it di-substituted. We can still get the di-substituted product by using a more bulky, sterically hindered base. You can see all the sterics and how bulky this base is, and we get that, di-substituted product 92% of the time. So why does a sterically hindered base favor the Hoffman product? Sterically hindered bases, also called non-nucleophilic bases, are useful in many reactions. That's because there's just more sterics involved. If we think about this, you have that hydrogen here, and you have the hydrogen here. To get the Zaitsev product, you're coming in here. It's more difficult to pull that off. And you can practice this on your own. If you have any questions, just let me know. Just remember, just remember what type of base you're using. Remember, okay, we have hydrogens here. So try to think about, which one's going to give you the di-substituted or the tri-substituted products, and does it make sense? So I want you to try that on your own. It says consider the dihydrohalogenation of 3-bromopentane, where 2 stereoisomers are possible products. Here it says we have the major versus the minor. Here is the cis versus the trans. Remember, trans, has more relief. And remember that example that we showed, this versus this. What was the difference? It was 4 kilojoules per mole, right? We're kind of seeing that, right here with this too. I don't know what the exact energy difference between those two are, but from that one example with those two on the top right that I'm showing, we know that difference is 4 kilojoules per mole. So, the trans is going to be, more stable. All right, I think this is a good time to take a break. So I will see everyone in 10 minutes. Enjoy your break, and I'll be back. I do apologize. I forgot to pause the recording. So if you're listening asynchronous, or if you decide to watch this lecture right after, you'll have to, well, fast forward through the 10-minute break that we just took. Usually I like to try to pause that so you don't have to worry about doing that, but I forgot this time. So I do apologize. So let's go on and share the screen. So hopefully everyone had a good break. Hopefully you're rejuvenized and energized for the second part of the lecture. I think it's even important for me to take the break too, in all honesty. Let me get my pen back. We just talked about the cis and trans and why that was here. So it says consider the dihydrohalogenation of the alkyl halide below. So here we have our alpha group, beta group, and then here would be your gamma right here, and beyond gamma would be delta. It says there's only one beta hydrogen to be removed, right? This is not a beta hydrogen right here. This is not a beta hydrogen, but this is a beta hydrogen. So you might imagine that it would be possible to form both the E and the Z alkene products, but only the E isomer is formed. So it says only the E isomer is formed. So this would be the Z. It says to rationalize the stereospecificity of the reaction, consider the transition rate state for the reaction. In the transition state, the carbon hydrogen and carbon bromine bonds that are breaking must be rotated in the same plane as the pi bond that is forming. In other words, the beta hydrogen, and here's your alpha carbon, here's your beta carbon, so this is the beta hydrogen, and the leaving group must be coplanar. That means within the same plane. So there are two rotamers where the beta hydrogen and the leaving group are coplanar. Since we are comparing two different rotamers, the Newman projections are a good tool to look at them. You can see they're coplanar right here. So the lower energy rotamer is the anti-coplanar. The syn coplanar is the higher energy rotamer. The product resulting from the anti-coplanar rotamer is formed and that's due to the energy differences. So we have the staggered, we have the eclipsed, and they're in the same plane on both of them, but one is staggered and one is eclipsed. Since the anti-coplanar, the staggered is the lower in energy, that's the one that's going to be formed. When you have all this stuff, these groups are going to have a lot of pushing on each other, right? So, if we remember our energy diagrams, the one will be high in energy, one is going to be lower in energy. So we're going to preferably form the one lower in energy. And who knows, this one even might be down here, and this one might be way up here. So which one's lower in energy? We're going to pick this one. It says evidence suggests that a strict 180-degree angle is not necessary for 82 mechanisms. Here, what they're talking about here is this is 180 degrees apart, and they're saying that this is not necessary, that a strict is not necessary. It says similar angles are sufficient. Well, if you look at 175 and 179, it's pretty close to 180. And the term anti-periplanar is generally used instead of anti-coplanar to account for slight deviations from coplanarity. Although the E isomer is usually more stable because it is less sterically hindered, the requirement for an anti-periplanar transition state can often lead to the less stable Z isomer. And I'll repeat that one more time. It says, although the E isomer is usually more stable because it is less sterically hindered, this would be less sterically hindered. The requirement for an anti-periplanar transition state can often lead to a less stable Z isomer. All right. So, assuming they proceed through an anti-periplanar transition state, predict the products for the following reactions. So you just have to arrange these where they'd be, anti-periplanar, which would be about, 175 to 180. It says for the following substrate, the beta carbon has 2 beta hydrogens. So here we have 2 beta hydrogens. There are 2 different rotamers where a beta hydrogen is antiplanar to the leaving group. And so 2 stereoisomers will be formed. Here we put the R1 in this position, and here we put the R1 in this position. In this case, the reaction will be stereoselective, but not stereospecific. E2 elimination will be stereospecific only when both the alpha and beta carbons are stereocenters. And you do have to know what a stereocenter is. It is on the test. And it's not going to be this way for this one because think about this, we have 2 of the same right here. So that's not a stereocenter right there. So it's very important to understand the difference between this term stereospecific and stereoselective. So in a stereospecific reaction, the substrate is stereoisomeric and results in 1 stereoisomer as a product. In a stereoselective reaction, the substrate can produce 2 stereoisomers as products where 1 is the major product. So I'll just leave it right there so you can think about it and write down some notes. So consider the dehydrohalogenation of a cyclohexane derivative where the leaving group is attached to the ring. So, okay, we have this leaving group attached to the ring right here. Given the anti-periplanar requirement, E2 elimination can only occur when the leaving group is in the axial position. So this would be in the axial position. Elimination cannot occur for this one. Because in this, it's not anti-periplanar right here, is it? And here it is. And let's just go back to the definitions of that so you can see that again. So anti-periplanar is slight deviations from 180. So we're saying 175 to basically 175 up to 180. And we can see that if we draw out the Newman projection, we get this angle that we're looking for. Here they're showing it as 180 degrees, but we do know that there's going to be some slight variations to that. So it's not going to occur right here because, you know, what's this angle right here? You know, that's not going to be 180 or 175. That's going to be much less than 175. So I got my calculator out. I'm going to use it today. So, you know, this might be, you know, 135 degrees. So, you know, if this was, yeah, so about 135. So somewhere between 120 and 180. Because, you know, there could be some slight deviations to that. So what they want you to do is draw Newman projections to see, you know, which one, you know, might happen, which one will not happen. And we're going to get, you know, we have we do have a lot of homework questions, so we're going to get a lot of practice, you know, rationalizing, you know, why products form. So we'll take a look at that further when we get into our homework questions. It says there are many factors to consider in order to correctly predict the products of an E2 reaction and decide what the major product will be. Now, will the substrate react stereospecifically, or will it be a stereoselective E2 reaction? Will the substrate produce several regioisomeric alkenes? If so, what will be the major product given the steric hindrance of the base that is used? And, you know, it says the only way to master is to do lots of practice problems, and we do have, you know, lots of practice problems with our homework. It says consider the following reaction where substitution and elimination products are formed. I should have put this as OET. So we either have that or we have that. So we have one of two things happening. The substrate is tertiary, so SN2 substitution is not possible. So we're not going to get this. The reagent is the, you know, ethanol, which forms ethoxide, which is not a strong base, and so E2 elimination is unlikely. It turns out the formation of the substitution elimination product follows first order kinetics, which confirms neither SN2 nor E2 as occurring. So you're saying that, you know, we're not going to get SN2 or E2, but it's going to be not. So now we're going to go into something called SN1 and E1. So that means, you know, we might have to have a good leaving group first. So this is your stepwise. SN2 and E2 are concerted. That means it happens at the same time. So now we're going to go into stepwise. So first something's going to leave, which would be the leaving group, which is bromine. So this is the first step. Bromine's going to leave. And once bromine leaves, it's going to form this cation. And now the products can either come in like this, or I'll just draw it on the same side that it has it, so that way you don't get confused. Or this ethoxide can take it right here, and you're going to form, and this should be hydrogen right here. And you're going to get that double bond here. So this would be an example of an SN1. This is your E1 reaction. So you can see, you know, the first step, we have the bromine leave, and then we form our carbocation. And we have two choices. We can either do an attack, which would be an SN1, or we can do elimination, which is an E1. So there's your two other choices. So you have a total of 4 reaction mechanisms that we learned today. You're at E1, E2, SN1, and SN2. SN2 and E2 are concerted. Everything happening in the same step. E1 and SN1 are stepwise. And then they show exactly what I showed on the previous slide, where you have the bromine as a good leaving group. And you can either go on to an SN1 and an E1, and we talked about that. Any questions on this then? You have a nucleophilic attack. You get the substitution product, or you can have the elimination product. So they're saying it's 3 steps. Okay, here's your first step, your second step, and then your third step. They're saying that this is the last step is just a proton transfer. So we have a proton transfer. This is called solvolysis because the nucleophile is also the solvent. So we can see that this is a nucleophile. It's also acting as the solvent too, as doing the proton transfer. So the highest energy transition state in SN1 is for the formation of the carbocation intermediate. So we see that right here. So formation of the carbocation is the rate determining step. We call that the RDS, the rate determining step. Any questions so far? I'm not seeing too many questions. That's why I want to give you the opportunity to ask me. And since the formation of the carbocation requires only ionization of the substrate, the rate of its formation depends only on the substrate. So the reaction follows first order kinetics. Now, if it would involve both, that'd be second order. But since it only involves a substrate, and what was the substrate right here? This is your substrate right there. And it only involves the bromine leaving. It says now it is clear that when substitution occurs by a carbocation intermediate, it is called SN1. So substitution, nucleophilic unimolecular. And they show the same thing again, the loss of the leaving group, the nucleophilic attack. That's pretty much it. It says if the nucleophile is a neutral species, such as an alcohol, there will be a proton transfer after a nucleophilic attack. And we saw that proton transfer, didn't we? We saw it right here. This is where the proton transfer occurred. It says the elimination reaction of a tertiary substrate. Okay, how do we get tertiary? 1, 2, 3. And an alcohol solvent like ethanol proceeds through a 2-step mechanism. Okay, we saw that. Loss of the leaving group, beta hydrogen elimination. Well, how do you get beta? Alpha beta. So even though that the leaving group was right here, right? This was the bromine. Oh, that's not what I wanted to do. The bromine was here, bromine is gone. This is still gonna be your beta carbon. And here you have the elimination product. And we talked about that, but they draw it in a better picture, but I thought mine wasn't too bad. So like the SN1, the E1 mechanism is still a first order rate because it depends on the substrate, the bromine as a leaving group. And it says right here, both E1 and SN1 share the same rate determining step. The only difference in energy is right here. And this is a lower energy product right here. So this is your major product. So in this case, SN1 would be the major product because it's lower in energy. It says because SN1 and E1 reactions proceed through a carbocation intermediate, a carbocation may rearrange from a 1,2 hydride, or I don't know why they call it methide, it's methyl shifts. You know, we're gonna, you know, if we have a good leaving group right here, you know, you may have a hydrogen here that you're gonna move over is what they're saying. So if that hydrogen moves over, now I'm gonna draw this kind of pictorially. Now we have that hydrogen here and the carbocation is here now. And why might that happen? Because remember, a tertiary carbocation is more stable than a secondary carbocation. Oh, for some reason. Oh, that's not what I wanted. So we have a tertiary versus secondary. Tertiary is going to be that's going to be the more stable. So this is going to be your more stable product. Here, if this was your leaving group, you have that methyl shift right there. So if you have if we do this, right, we have this right here, we have a cation. Well, you know, we have we have a secondary versus, you know, now we're going to shift that right there. Now we put the cation here. This is a tertiary carbocation. 1, 2, 3. So tertiary carbocation is more stable than a secondary. So think about how you may get shifts is what they're trying to tell you. And the reason why that can happen is because it's not concerted. It is a stepwise you know, reaction for your SN1, and it's also stepwise for your E1. So like I said, there are a lot of, this chapter is just, there's a lot of stuff going on, you know, a lot of information to take in. So it says when it's tertiary substrate is reacted on our isolysis, you know, we just talked about that. The solvent acts as a nucleo and acts for proton transfer. Only the product resulting from rearrangement is observed. Remember, primary carbocations are too unstable to form. So in this case, rearrangement occurs as a leaving group leaves. So this is happening at the same time. Right, so experimental data indicates SN1 and E1 reactions are faster in a polar product solvent. So relative rate of methanol, relative rate in DMF. It says rate, the double star says rate of reaction is measured by using an isotope of iodine. So what is an isotope? Some people may have forgot it. I had seniors forget what this was. So an isotope is, same number of protons, different number of neutrons. So that's what an isotope is. So basically what they did was, I don't have my periodic table with me, but I'm just going to make this up. This is totally made up right now. So maybe you have an isotope. Let me just look this up real quick. I don't want to make up my numbers if I don't have to. So I'm going to look up different isotopes of iodine. I haven't really studied iodine too much. That's why I don't really know them as well as some other ones. Different. So there's 34 different isotopes of iodine, and in nature, you have I-127 and you have I-129. So let's just say I preferentially label it with I-27. You could choose I-29 too, and you're just watching the transfer. So let's just say this is I-127. We're watching that I-127 come off. Relative rate in methanol and a product solvent. Here we have 43, and here we have 6,500. So it's going to really prefer to be in a polar A product solvent if you want to push that reaction really quick. And this is SN2. So if we wanted to have it SN1, we'd need it to be in the polar product solvent. Overall, for SN2 reactions, a polar A product solvent is best, and we saw that with DMF. For SN1 reactions, a polar product solvent is best. So those showing you the difference in energy diagrams for a polar product, polar A product versus a product. So A product solvents raise the energy of the nucleophile, which results in a lower activation energy. So let's think about that. So A product solvents raise the energy. So we raise the energy here, which results in a lower activation energy. So here's your EA for this one. Here's your activation energy for this one right here. So, let's just say this is 1. And to go down here, this is 4. So that's a difference of 3 units. Product solvents stabilize their carbocation intermediate. If you have some type of carbocation intermediate, a polar product solvents will stabilize that. Which results in a lower activation energy. So we can see this activation energy is much lower than this one by about, I don't know, a third or a half, and a faster SN1 reaction. And our next slide will be the last slide for today. We've done a lot. So the better the leaving group, the faster the SN1 or E1 reaction. This would be the most reactive. We have to think back about what was the strongest acid, and then we think about the conjugate base. Remember, the rate determining step for SN1 and E1 of the alkyl halides is the ionization step. So the formation of the carbocation and halide ion. And reactivity towards SN. And why is this? Think about this now. If I have this thing right here, I have iodine, and I have the same thing. I have fluorine. Well, what's going to be a better leaving group, fluorine or iodine? Well, iodine is going to be a better leaving group because, one, it's just a bigger atom. It's going to be able to take care of itself better on its own. Here, it's smaller. It's not going to have the resources, to take care of itself on its own as much. So here we have a bigger atom. It's going to you know, be able to take care of itself better on its own, you know, it's going to be able to leave, and, you know, it doesn't matter, and it's going to form that carbocation right there. It's because it's a better leaving group. So I do want to leave off right here. I'm going to stop sharing, stop recording. So everyone have a great day. If you have any questions, please feel free to stay by and I'll try to answer them. So thanks and have a great day.